Teach me about the Great Lakes. Teach me about the Great Lakes. Cha! Welcome back to Teach Me About the Great Lakes, a twice monthly podcast in which I, a Great Lakes novice, the old GLN, ask people who are smarter and harder working than I am to teach me all about the Great Lakes. My name is Stuart Carlton, and I know a lot about the tablet drums that emit from your radiator right when you want to start recording. Making it very challenging to start recording unless you turn up the heater to the extent where you start to sweat during the recording. Maybe sweat enough that you can hear that in the microphone.
Ew.
But I do not know a lot about the Great Lakes. That's the purpose of this here show. We're joined today by the one, the only, the special Megan the Lake Lover Gunn. Megan, how's it going?
It's going well. It is cold outside, but I also have experienced wearing my coat and speed walking.
Yeah.
And then all the sweat in this
The sweat.
15 degree
Yeah, I got
weather.
this electric vest thing. So sweet. Anyway, we're also joined today by the big tuna himself, Natty Morrison. How's it going?
Oh, it's going great. Loving it. Love that that's my new nickname, by the way. Am I showing on the screen?
I don't know. Did you join in? I will add you.
I did.
Okay, yep, there you are. Yeah,
Okay,
there's the big
great.
tuna. All right,
Yeah,
good.
I don't know what to say about the nickname. I regret having ever told anybody that.
Okay.
So.
We love this story.
Fair
I
enough.
love this story.
I told you I tried. So Natty let it out that he every now and again, not every time, would when he's making tuna, he would just take a little sip of the tuna juice, just to try it and to not waste it, right?
Yeah.
And so
yeah, I
since
did
then-
say that.
Yeah.
And now it's become a point of conversation about this. My fiance was like, you just need to be careful about revealing weird stuff about yourself because, you know, you reveal one weird thing and then the next thing, and then you're the weird guy who's drinking tuna juice and all the other. And I was like, it's just, I feel very regretful of this. But
The thing is,
I love being introduced this way.
Yeah.
It's very nice to meet you, Eric.
yeah. The thing is this, though. The thing is this. In between now and then, you know what I did? I tried a little bit. It
Yeah?
was good.
It's not bad, right?
No, it's good.
It's not bad.
Yeah, I tried it. Anyway,
great.
so I don't know it's a recommendation. But anyway, that's not the point. We like to open our show every week with a Ask Megan question. If you have an Ask Megan question, send it to teachmeaboutthegreatlakes@gmail.com. This question is this. It's from the Great Les. Megan, it is the season of love, and you are known as the Lake Lover.
That is my nickname.
That's right. If the 5 Great Lakes were suitors on The Bachelorette, which I've never seen, but that's a TV show where you get all these bachelorettes and you get one bachelor typically, and then he gives them roses, right?
Yeah.
And then he says, you were the bachelorette for me, and then I'm not sure what happens after that.
Yeah.
Anyway, who's getting your final rose this year? Which lake? And who's going home crying in the limo?
So it would have to be Lake Michigan.
Lake Michigan.
Lake Michigan is my forever love.
Forever love.
It's where I grew up and playing in her lovely waters in my backyard.
Yeah.
And I would have to send home Lake Erie probably because
Okay.
Would that be the first one to go home?
probably yes.
Yeah.
Okay.
If I had to choose, that's a great question. If I had
is a good
to
question.
choose, like I had one final rose and it would be between one and the other, I don't know, maybe
Erie-
Lake Huron.
Yeah. Erie would be watching from home. Is what you're
Yeah,
saying.
yeah.
Yeah. You
Well,
trust the process.
There it is. There it is. If you have a question for Megan, send it to teachmeabouthegreatlakes@gmail.com. But that's actually not the reason that we're here. Nope, I'm supposed to say that later. Instead, what I'm going to say now is we've got a cool interview lined up today. I saw this paper come out. That's not true. I saw this paper a bit after it had come out, kind of a cool thing on lake ice. And I said, we have to talk about this. And I saw that the authors on the paper, which I am about to find the link to, sorry, Eric Anderson, Google Scholar, so I get the name right. But the authors on the paper were 2 former Teach Me About the Great Lakes guests. So I said, we have connections. And the name of the paper will be something that I give you very soon.
I just put it in the
Did you?
file.
Aren't you fancy? All right. Thank you.
You're welcome.
I should have had that. What happened? I thought I had the link in there.
It was in the email.
Anyway, about the relationship between, all right, I don't remember what I said. So I was going through trying to, I like to keep up on the Great Lakes news. It's what I do. It's part of my job.
Yeah.
And so I saw this paper by our old friends Eric Anderson and Drew Grunwald. about ice cap cover. This is out just a couple months ago in Geophysical Research Letters, which is a fancy sounding journal. I like any journal that's like letters, because it's like you sit around in your tweed jacket and you compose letters and you send them off. But anyway, this is called Does Ice Cover Cap Evaporation in Large Lakes? Anyway, so it's about this relationship between ice cover, which has been super low in recent years, so not this year, and evaporation and lake stuff and lake levels and all this. And so I was like, this is perfect for us. So I called up Eric and I said, Eric, we must go on the show. And Eric said, yes, we must. But first, of course. Researcher feature. A feature in which a researcher gonna teach us about the Great Lakes. Our guest today is Dr. Eric Anderson. He's an associate professor in civil and environmental engineering and the director of the Hydrologic Science and Engineering program at the Colorado School of Mines in Golden, Colorado. Eric, thank you for coming on.
Yeah, thanks for having me back.
Yeah, this is great. Eric taught us all about modeling a few years ago. The episode was called A Million Little Triangles, I think. And so Eric does a lot of modeling work, which is increasingly critical to everyday life, frankly. But here we are to talk about your paper. So first, we have a new segment, which I'm renamed Explain It to My Grandma. And so what we want to do is we've learned that naturally, the further we go on, the more people start, they start listening in a commute, and then the commute ends, and they maybe... We want to get to the good stuff first. So explain it to my grandma with the slight caveat that all my grandmas are dead. So we need to explain
it to Megan's grandma.
Explain it to Megan's grandma.
Yeah.
My grandma would not be go nuts. Anyway, so in 60 seconds or less, what does this paper say?
Okay, I'd say if you're like me and you put a coffee cup on your desk filled with coffee before the semester break, and then you leave and come back, in January, and the coffee is evaporated and left is like a dark, weird stain at the bottom. That's because that coffee evaporated up into the air, right? And you could have stopped that by maybe putting a lid on it, and then I guess drinking it when you came back a month later. But the liquid, the coffee would still be in there. And so if we think about that analogy in the lakes, when there's evaporation happening, which is pretty much in the wintertime, ice could be that lid. And it's easy to think about it being that way. And basically what we find in this paper is that it's not so simple. Our ice lid really just has a bunch of holes in it. And so it doesn't keep that water in the lake.
Boom. Done. All right. Thank you. Yeah. Great. So let's go into detail. So, So this has traditionally been the story that there's a strong relationship between ice cover and lake level. And heavy ice cover means less evaporation and therefore higher lake levels. And that's always been kind of the story. Now, was there science to back that up, or was that just an assumption based on metaphors like your coffee cup metaphor?
It makes sense on a couple levels. I think one is that lid metaphor still holds on a certain scale. I guess that's the caveat. But like if you have some water and you block it with something like a chunk of ice, yeah, that water's not evaporating up into the sky right at that point. And then also all this stuff is tied together with the atmosphere. And so you have kind of warmer climates and therefore less ice and there more evaporation happening. Like all that is real and happening. And so the science is there. I think what is important is the nuance, actually how that plays out. And in the Great Lakes specifically, or I should say maybe just big lakes. So this isn't a small lake thing. We can talk about why those act a little different. But the nuance there and how that plays out actually is kind of the surprise, I guess.
So when I was going through the paper, it made me think like if the ice was completely covering everything, that like our lid example, that would be one thing, but that's not really what ice is doing, right? Like the edges aren't necessarily fully covered and the ice is moving. I heard a lot about shelf ice recently, and so the ice is moving and things are exposed. So does that play a part in what's actually happening in reality, or how we thought what was happening is not necessarily happening anymore?
Yeah, no, absolutely. So on a small lake, I think it's easy to picture like a pond scale, let's say, something you can see across. And in the winter, those pretty much get frozen. One's up north enough. Those get frozen over solid, basically. You can walk across it and it's probably safe. And in that sense, that's a nice lid example where that is plugging up the evaporation and really shutting that down. In lakes as big as the Great Lakes, full ice coverage across the whole lake doesn't really happen.
Yeah,
okay,
it's
so
rare if ever, right? Yeah.
yeah, we'll say I haven't tracked it. I don't have a stat in front of me. I remember a few years ago when like Superior maybe iced over for a few hours, and it was like this first or second time in 40 years. And even then, there's probably some open water somewhere, but like largely it looks like it's frozen over. So, but the general rule is it doesn't really happen for most of the lakes. Erie is kind of the exception where it gets heavy ice cover in most years. Ontario almost no ice cover in most years. And Michigan, Huron, and Superior are kind of a mixed bag, but not getting to like a full ice coverage like you see on a small lake. And so you're really never in a situation with these size of lakes where you have complete ice cover. And I think that's a little surprising to probably anybody not looking at satellite images. If you go to the lake shore and look out, and you might see ice in a good ice year, like as far as your eye can see, and it just feels, and it's wintry and cold, and it feels like it's just an ice covered lake. But the reality is that probably, and again, in Superior, Michigan, and Huron, only extends so far, and then you have open water out in the middle. And so that shoreline perception, I think, is can be misleading. That again, that kind of like space scale view of what's happening, or at least plane scale if you're flying up over top of it, isn't easy for most people to see and I think get a feel for.
Is that why you chose the modeling approach? Because this is something different than
well,
what
just
our
what
eyes
even
can
got
see.
you? Yeah, what even got you? Let's take a step back even from there, right? And what even got you thinking like I want to study? So I want to study this. This is what I want to do. Like, how did you get to think that maybe this is something you could bring your modeling approach to?
Yeah, I'll say that the conversation that led to this whole thing happened at the Great Lakes Conference,
There it
IAGLR,
is. Yep.
2 years ago in Windsor. So sitting there talking to my co-author, Drew Gromwald, and this idea came up, and that led to a conversation about what do we really think is happening? Do we think ice plays this role? And the reason we even said that is because that concept gets mentioned a lot of times. So I think you see it, maybe on the news when it's being covered in terms of like the weather report or something about Great Lakes ice and what that means for lake levels and evaporation. And then, but we were even at a conference where we heard people say it there, like, okay, well then ice formed and it shut down the evaporation.
Yep.
I'm sure I've said it too. And
People have said it on this very show. But anyway,
I should check that. So I think we just started thinking about if that process really would play out that way in the Great Lakes. And partially we actually started from a slightly different angle, which is not even thinking about the full ice coverage piece, which ended up being the important part here. But just like in the winter, in a cold winter, that cold air just doesn't hold as much water vapor as a warm air does. That's kind of the climate change problem, right? So as the air warms up, it can hold more moisture, and therefore it can suck up more water from lakes like these. In cold, dry air, although it may be dry and can suck up water, it just doesn't have the capacity to hold as much. So like I was in class, I'm always like, imagine if your water bottle suddenly like got bigger in a warm air situation or in a cold air situation, it gets much, much smaller. It can't hold as much. We actually started with that angle, but that led to us going, okay, let's figure this out. And the way to do that, really on lakes like this scale and everything, is modeling. We just can't get the observations that we need to capture every angle. And we can talk about what obs are out there, which are pretty cool and unique, but really this became a modeling scenario and kind of a what if. And with models, you can do some magic sometimes, like make unrealistic things happen for the purpose of, kind of testing it. And so that was a pretty easy and fun pathway for this to play out.
And so you all did that, and you came up with like actual answers. We are now able to see how ice coverage is actually impacting our lake evaporation and our lake levels.
Yeah, totally. And, I think we actually came at it from a couple ways, and the modeling was one, and I'm mostly a modeler. And so everything's like a modeling exercise for me, but we actually, we have satellite observations of ice cover going back to, the dawn of satellites. And before that, it was observations that are always confusing to me how they got those. But back in the 70s, Noah Glurl has records of that going back to the 70s.
it involved a captain and a bottle of whiskey, I think.
And we have, now evaporation's a tricky one. We don't have like good direct measures of like whole lake evaporation. That We just can't get that. But my co-author Drew has a fancy statistical approach to try to come up with what the lake evaporation is monthly, again, going back 50 years or something. So we started by looking at those data sets and just said, like, okay, in big ice winters, do we have big evaporation or small evaporation? And same thing when it's mild winters out there. And the data actually shows us that, yeah, ice, doesn't have, it's not like ice forms and you shut down evaporation. We weren't seeing that. And that got us looking at, like, okay, it's just this partial ice question, or like, you got holes in your lid, that must be what's going on. And then we could use the model to say, okay, is that really what's happening?
And this is a question from somebody who is, I wouldn't even say a modeling novice, somebody who's maybe doesn't understand what modeling is, but what exactly goes into developing a model like this?
Okay, I'm going to talk to the physical side stuff that I did, because the statistical model that Drew worked on is too fancy for me to explain what happens there. Sure. I'll say it's Bayesian statistics, and I'll stop with that word. On the physical model side, so I think it's a combination of, like, we in the physics world, we're blessed with having some governing laws, right? Not like the biology world where things are very complicated and we don't have these kind of, I think, things to rest on. So we start with, like, some fundamental laws that tell us that mass is conserved and energy conserved and things like that. And then we pull in data sets that help us with some of the empirical kind of pieces that we just aren't smart enough to solve for ourselves. And so an easy one to think about is like turbulence. We just don't understand turbulence, but we know it's important. It mixes up things. And so we can kind of parameterize that effect using some observations or experimental approaches that somebody took. So that's kind of the backbone of these models, is we have these, like, fancy equations that we think govern how the universe works and how the lakes work and everything. And then where we can't quite solve or get the physics detailed enough, we stick in some observations. Like, well, here's what we saw. Here's how wind and evaporation interact. And we can stick that in the model, kind of in surrounded by some good kind of Newton-esque solutions to equations and help figure this out. Specifically, what goes into that for this case is, like, tell me the air temperature above the lake, the solar radiation coming down, the humidity right above the lake, so how moist it is up there. And if you tell me that, we can run these models of the lakes, and it will tell you back what the water temperatures are, the currents, whether there's ice or not, and kind of try to predict those things. So that's kind of what goes in and what we're trying to predict out of that model. And
is there a need to effectively, like, is there a prove it sort of deal? Like, how are those models then verified as being like, yeah, that worked, this is accurate, or how does that work? Yeah. So in this case, we're relying on some proof that the model works for doing the kind of, like, bread and butter things it's supposed to do. Mm-hmm. And then we used it for some wild, unrealistic scenarios in this paper that we can't measure, and that's where the model's handy. But to, like, what do we compare that to? So the model's predicting water temperatures. So we can measure water temperatures from space on the surface, and we compare the model to that. That is wild.
I say we, like, I'm not doing that.
No, it's like, I am assuming that it's you. Today, later, when I talk to somebody, I'll be like, yeah, dude, I met the czar for water temperature.
And we also stick things in the lake, put thermometers in the lake all over the place, and from top to bottom in some places, and buoys are measuring water temperature. So we have these, like, in situ measurements of what's going on. In this case, temperature is the big important piece, but the same happens for currents and water quality parameters and stuff. Ice you can see from space, so we can kind of get a good idea of how much ice coverage is out there and if the model is predicting those things well or not. So that's really how we, like, build some confidence that this model's acting, like nature would have it.
Excellent.
And so then with that, so what you found, like, big picture, is that these atmospheric conditions are really a bigger contributor than ice coverage, right? Was that fair to say based on your findings?
Yeah. If ice was totally covering the lake, that would be a big important thing, of course. But I guess that the atmosphere is driving it, which, like, isn't surprising, right? I guess that piece is like, well, of course it is. We would think that, but it gets at that. It kind of refocuses what people normally think was ice is blocking the evaporation. It's like, well, no, really, the atmosphere is controlling everything. And so there's a couple of interesting things about that. One is, like, when you have a lot of evaporation in the fall in the Great Lakes, that evaporation cools the lakes. So the lakes are cooling down because that's happening, and it can drive them into a heavy ice season, right? Just so you have high evaporation that leads to high ice, like that kind of ordering, I guess. But the other piece of it too is that the atmosphere is, if that air that blows over the lake is dry and has room to suck up moisture, that's going to happen, right? If that air is kind of close, saturated in somewhat, doesn't have as much room for any more moisture, then moisture is not going to transfer, whether or not that's open or not. So the atmosphere is the big driver here, and the important pieces are like that humidity, and then the wind speed, right? So like when you blow over your bowl of soup to cool it down, right? You are doing what that wind is doing to the lake, and you're kind of like accelerating how much heat can be pulled out of that bowl of soup, and therefore the wind's doing the same thing in the Great Lakes. So the faster that blows, the more heat it pulls out of the lake. And so those pieces are really important. Then the ice kind of responds to those things. So the ice, it's not insignificant, but it's not the dominant storyline.
Okay, so have you found, and I think that this is related, if we have we had a super hot summer, we still have super hot Septembers and Octobers, does that change the evaporation and the ice cover that we're going to get later, or does the cooling happen regardless and that's not necessarily affecting the ice cover? Does that make sense?
Yeah, great question. So we kind of had it this year. So in the fall, the lake temperatures were quite warm, extended into, I don't know, September or maybe even October, warmer than typical. And the question was like, what does that mean for ice? These lakes are hot, basically like hot relatively. And so what's going to happen? And it really all depends on what the air and the atmosphere does now. And so like right now, we've been in a cold blast in the Great Lakes that has formed all this ice, even though we were with really hot water in the lakes in the fall. So it's like the air can change everything. Right. And so what you had with those warm lakes in the fall, right, that they were warm, cold air comes across, you're going to get a lot of evaporation. So that might boost that signal at that time. But depending on what the atmosphere does in, say, January and February, that will dictate basically how cold the lakes get, if they get to an ice state and all that kind of stuff. So that's what makes like projecting these things out so hard, because you could say, well, we're hot in September. Does that mean we're going to have low ice in January? Well, it depends what January's atmosphere does.
Interesting.
All right, we are going to take a little break. When we come back, I'm going to have some shocking Great Lakes factoids about lake ice that Claude has been crunching in the background while Eric has been talking. And Eric's going to tell us what his work means, and then we're going to play the most exciting game maybe that's ever been invented. You're listening to Teach Me About the Great Lakes. All right, we're back with Eric Anderson. You're listening to Teach Me About the Great Lakes, twice monthly podcast in which I ask people to teach us all about the Great Lakes. Stuart Carlton, joined by Megan, the Lake Lover Gun, Natty Shaw Morrison.
Thank you.
Yes, you're welcome. He was afraid I was going to call him the Big Tuna.
You just did.
We're talking with Eric Anderson today about a cool paper he did that I don't know, maybe it's overstating it, might revolutionize our understanding of large lake ice processes, which is pretty amazing. And he's going to tell us what exactly that means. But first, we got some cool Great Lakes lake ice well, now, hold on. I might not be able to give you these because, I'll be honest, I don't believe what Claude is telling me.
Well, that's what they're unbelievable. Just say them.
Literally unbelievable lake ice coverage. So instead, I'll do this. All right, here we go. Instead, what I'll do is you can go to GLERO, the Great Lakes Environmental Research Laboratory, where they have ice cover data, and it can show you the current conditions where ice cover is actually pretty high right now because it's been freaking cold. But then they also have maximum ice cover plots. And so Eric was talking about how recently Lake Superior might have been close to 100%. And here's what I'm going to say. I'm going to give you a Great Lakes factoid about lake ice and Lake Superior. But first, it's a Great Lakes factoid, a Great Lakes factoid. It's a great factoid about the Great Lakes. Cha. Lake Superior did reach 100% ice cover in 1996, March of 1996. The time Eric was probably thinking of would have been 2019, got to 94.9% 2019. Lake Erie. I should run a, you know what, I'm sorry. That's how I got to do it. Lake Erie. Lake Erie has reached 100% ice coverage 3 times since Clairol began tracking in 1973. Most recently in 1996 in February. So about a month before Lake Superior. So there you go. Lake ice coverage. Pretty cool. All right. So, Eric, if I'm going to sum up your paper here for Megan's grandma, I will do it less eloquently. But basically, people thought that the amount of ice coverage was a really large determinant in evaporation and therefore lake levels. And what you and your colleague Drew Gronwald found was that while ice coverage plays a part, atmospheric conditions play a very significant part too, and maybe even a bigger part depending on the specific year and the specific conditions. So that strikes me as completely changing our understanding of how this process works. Some academics would say this changes forever, blah, 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 blah. And the others are more humble and say, well, if you made incremental, all right, you could be either kind of academic. They both work. But so what does this mean? Like, what is this both for your field, but then also for people going forward? Like, how do we use this info?
I think the important piece here is when we think about how lakes like these are represented in, say, big global climate models, the things that are projecting 100 years out, what's going to happen, these kind of scenarios. The lakes are represented really poorly. Like historically, well, I don't know. At the start, they weren't at all included on that map. It was like continents and ocean. And then they started adding lakes, and they were like these little blocks, so maybe Superior was 2 blocks and everything else was 1 block. And they actually, this is like a historical tidbit, they assigned the temperatures of the lakes by averaging the Atlantic Ocean and the Pacific Ocean.
Oh, because it's right in the middle. Yeah.
Yeah. So, that worked well. Now, they've improved since that, but not by an outstanding amount, I would say. There's still room to grow there. But all that said, I think the way that we even model these lakes, and we're lake modelers and lake lovers, and we're trying to do our best, is that ice, like the way that the models work is like you cut off the evaporation proportionally to how much ice there is. So like in a spot in the lake, let's say, the size of your desk or something, if you say that chunk is 50% covered, then the model's going to say, okay, well, reduce the evaporation by 50% in that chunk. And if it grows to 100%, reduce it by 100%. And that's fine if you then have a chunk next door that's open water and you're resolving that at the right scales and stuff. These climate models, because they're global and therefore they don't, have real fine scale resolution and stuff. Again, these lakes are poorly represented. They are using these kinds of fractional approaches that say, okay, well, if Superior is at 50% ice cover, then reduce the evaporation in the atmosphere by 50%. And that just, I think, is the problem. That kind of simple, kind of proportional math just doesn't capture that level. And so if we want to get kind of the climate scenario, the climate story, modeled accurately, we need to represent these lakes better. And that kind of simple ice math, I think, is the piece that needs refined.
That makes sense. There's a really great example, but it doesn't mean that before. Well, there's that very famous saying, multiply attributed, but I think it's an important one, which is that all models are wrong, some models are useful, right? And I think what I remember you talking with us before is one cool thing about modeling is it forces you to really think about what affects the system, what assumptions you make, what information you have and don't have, and how do those relate. And in creating those models, that becomes pretty dang useful. But so while at first that was a good first run, maybe not that good of a first run to average the Atlantic and Pacific, now as science advances, as computing power advances, as our understanding of statistical inference advances, you can get a lot more accurate. And so, yes, the model is probably still wrong in the sense that it's not super precise, going to predict what it's going to be like. It starts to become really even more useful, right? And so then you can have more useful information into additional useful models to help explain where we're headed. And long term, I think that really helps. I think there's a policy story there, too.
Yeah, absolutely.
Yeah. Excellent. Well, it is time for our game. This is so exciting. We don't have any game theme music, I realize. The only game theme music we have is the Wheel of Erie. Which is not super relevant, I'll be honest. So we're not going to play the Wheel of Erie, but we are going to play overrated or underrated.
Ooh.
All right, so we're going to present some things here. And then you are going to tell us, and then a sentence why. It would be super boring if you just gave us a word. Overrated or underrated. And if you want to say properly rated, that's fine. I'm a survey researcher, and so there's always a big debate: do you include a neutral point, or do you force people to choose? I don't want to force you to do anything, Eric. So if you want to, all right, Lake Lover, why don't you kick us off?
So modeling as a way to understand the world around us.
Is that overrated or underrated or improperly rated?
I'm going to say underrated.
Underrated.
This is why. I think there's a saying that I think is originally Einstein that's been adapted for, I think, the modeling world, which is everybody believes in observation except for the person who made it. And nobody believes in model except for the person who made it. And I think that's kind of the gist that I get, is that these models are kind of viewed oftentimes as, these black boxes that you don't know what happens inside. And so, what's going on with these things. And I think often, at least from the modeling side, I know all the bad parts about it, right? Mm-hmm. And so you're trying to avoid those and use it for something useful. And I think they can do a lot more cool things than we give them credit for, if you're careful, right, and how you use it.
Excellent.
Awesome.
Next up, lake ice.
Lake ice. Overrated? Underrated?
Oh, man. Okay, so I'm going to go at odds with this paper and say it's underrated.
Whoa! Underrated.
And the reason for that is I think it's really complicated. So, we've been trying to model lake ice for a long time, and people before, everything I do is just built on people that came for decades before, working and doing things. And it's one of the more complicated parts of the lake. It's tough to get right. It's wild out there. It's not like an Arctic ice sheet. It's all like the marginal ice zone. It's all this crunching, smashing, moving stuff that is, I think, how cool it is and how difficult it is. I think that's underrated.
Absolutely. Love it.
Love it. Plus, there's a huge cultural story with lake ice, which I didn't appreciate because we don't get any lake ice on our little neck of Lake Michigan. Or if we do, it's bad news. Has Lake Michigan ever had? No, nowhere near 100% cover. 92 is the highest I see in that data set. Anyway, but there's a huge cultural story with lake ice.
Whenever I see 100%, I always assume that that's like not true. Like I just realized that.
That's because you're making that observation.
Well, yeah, because they're like, it's 100% reliable, or it's 100% accurate.
100%,
yeah, or like when I see a product, they're like, it's 100% sustainable. I'm like, is it?
No, you have to have room for error.
100% OPSEC, whatever.
I checked all of it. It's 100%.
Yeah.
Like, so.
Every percent has been checked.
Yeah.
All right, here's one. You mentioned Bayesian statistics. This got me thinking. What about the concept of statistical significance?
I am not an expert, but I have a strong opinion on this.
That's what we're going for.
Yeah.
Love it.
Years ago, we published a paper, and we a co-author on that paper said, the American Society of Statistics no longer is talking about significance. Do away with it. And I'm paraphrasing. I'm sure I'm doing a bad job. And so we didn't put it in that paper, and the reviewers were like, you better calculate significance. What are you doing? And we threw these recommendations back at them from the Statistical Society and got that paper through, I'll say. So I'm going to say it's overrated with very little knowledge about the subject.
Fair enough.
It's also... It's an unfortunate acronym for the American Society of Statistics. Am I right?
Yeah. Potentially, yeah.
They, what is the likelihood of them not realizing that?
Right, 100%.
Dude, they're 100% now. They must. Yeah, for sure.
Yeah. No, I'm a big confidence interval, point estimate confidence interval guy, but it often is a big fight there. But yeah, well, and the other problem is nobody knows what a p-value is.
Those idiots.
I won't ask you, Eric. But yeah, if you ask your average faculty member, many of them would not define p-value appropriately because it turns out it's a weird specific definition. Anyway, bring us home, Lake Lover. Last one.
So since you work at the Colorado School of Mines, underrated, overrated, or neutral cryptocurrency mining?
Okay, I know not much about what any of that means.
You're at the Colorado School of Mines, man. I figure that's most of what y'all do.
I'm going to say that it is overrated, and I don't know if this applies, but just because I don't think we should be even dealing with that.
Yeah. Okay. We don't need you to go into detail there, but fair enough. I wanted to come up with some big mine safety thing, and I was like, I don't even know enough about the only mining I know is, and it sounds like Eric and I know the same amount about it. Well, anyway, Eric, no, this is great. We really appreciate you coming on and telling us about this paper, which, again, if I were your agent, would say is revolutionizing. No, I wouldn't. I would say it's revolutionizing the way that we conceive of large lakes and one of their most critical processes, which is the lake levels and the way the lake ice affects them. And it's interesting to hear the approach you took, and I love the work that you do and that Drew does. And you're all both great guests and all of that. But that's actually not why we invited you here and Teach Me About the Great Lakes this week. The reason that we invited you on Teach Me About the Great Lakes is to ask you 2 questions. The first of which is this, and we can look for precision with you since you have answered before. If you could have choose to have a great donut for breakfast or a great sandwich for lunch, which one would you choose?
So I think before I said sandwich, and I'm sticking with sandwich.
Sticking with sandwich.
Love it.
Oh, this is good. But you have moved since our last time. You were in Ann Arbor? You were Claro, right?
Yep.
Yep. You were in Ann Arbor. You probably said Zingerman's because they all do. And that's fine. No problem. But now you're in Golden, Colorado.
Oh, I love Golden.
I'm going to go get myself a Coors Banquet beer, and I'm going to carry it into a restaurant, and I'm going to drink it with a delicious lunchtime sandwich. Where should I go to do this?
So I would suggest Just Be Kitchen,
Just Be Kitchen.
which has some kind of buffalo-y chicken wrap of sorts that they call the riot wrap, which is delicious. So if wraps work in a sandwich, that's what I'm going with.
I would say yes, it is.
Yeah. We're not doing that here.
Yeah.
Sounds great.
And speaking of Golden, I lived in Colorado for 2 years.
Did you?
And I lived in Superior and then Denver for another year. And I didn't know that I was afraid of heights until I moved to Superior and went to Lookout Mountain in Golden.
Oh, yeah.
And I got up there and I was like, wow, I am terrified of heights. And then had to drive back down the other side of it with all the hairpin turns with my sister driving, who had just gotten her license in her 20s. It was a terrifying experience. And so I'll always remember Golden fondly for that reason.
Yeah, that's a harrowing drive. We've always remarked, like, the people who decide where they place guardrails are...
Dude.
It's confusing. Like, the sharpest, steepest turn has nothing. And some other stretch has one.
It is as though they are like, it's so scary that I would just drive off the edge. And let's just get it over with. Or it's going to happen. She would accelerate, brake, turn, accelerate, brake.
Yeah.
I think they just put them in. I think they just put them in retroactively. So like
Maybe they just ran out of metal.
goes over the side. I guess
they're actually in memoriam of everybody who's gone over there. It's like, oh, there's another one.
It sucks though because the family has to spring $1,000 to pay for the guardrail.
Yeah, it is. It's made by the metal from the car.
Oh, jeez.
Sorry.
Well, we have gone to a weird place, but we want to know, what is a special place for you in the Great Lakes that you'd like to share with our audience, and what makes it special?
Okay, so last time I answered this, which is with a great spot, which I said the Straits of Mackinac, which I still love.
Yep.
But it's only because I couldn't think of my real favorite place, which is maybe a ghost town, I don't know. But there's somewhere called Port Oneida, if I'm saying that right. And it's on Lake Michigan, on the state of Michigan side, just north of the Sleeping Bear Dunes. And if you drive up there, I think it must have used to been a place, because there's like a building with a historical sign that I honestly never read. But you can park at that building and sneak down onto the beach, right on this beautiful, isolated, nice sand beach overlooking Lake Michigan. You can see South Manitou Island from there. And so Port Oneida, which I probably just gave away that exists and people are going to go flock. But that's my favorite spot.
Awesome. Eric Anderson, Associate Professor in Civil and Environmental Engineering and Director of the Hydrologic Science and Engineering Program at the Colorado School of Mines in Golden. Thank you so much for coming on. Thank you for this cool work. And thank you so much for coming on and teaching us all about the Great Lakes.
Thank you. Glad to do it.
Megan, the Lake Lover, what's something you learned about the Great Lakes this week?
I learned that Lake Superior has had near 100% ice cover. That lake is so deep.
It's so deep.
It just that just is blowing my mind.
Because that water down there should act as a nice ballast.
Yeah. And how Lake Erie being fully covered, that doesn't surprise me. But
I just didn't know that. Yeah.
Lake Superior, whoa, mind
Well,
blowing.
you know what? We'll just have to have someone on to tell us. How could that happen?
Yeah.
How could that happen? Natty, what's something you learned about the Great Lakes this week?
I learned what modeling is, and so I feel like really what I learned is the depth of knowledge and ingenuity of the minds who are thinking about these issues and what they're capable of. Yeah. It is really remarkable to realize that they are able to put all this together, and then, you know, what that could mean for future generations as they continue to monitor the Great Lakes and learn more about how that works as in a general global climate model.
Yep.
Yeah.
Really cool. The way that there's a lot of people with really high functioning, rigorous brains thinking through this stuff, right?
Yeah.
In a very thoughtful way. It's pretty awesome. Pretty awesome to talk about people like that. Me, I'm usually just here for the fart jokes. Teach Me About the Great Lakes is brought to you by the fine people at Illinois, Indiana, Sea Grant, Illinois. And you bring the Illinois, Indiana's Sea Grant. We encourage you to check out the cool stuff we do at iicgrant.org and at ILIN Sea Grant on Facebook, the old Blueski, and other social media. Insta. We're on Insta.
Mm-hmm.
We're on LinkedIn.
Insta.
Have we been doing more LinkedIn? That was my understanding.
Oh, yeah.
You should follow us on LinkedIn.
Yeah, absolutely. Get that connection in there.
Let's connect, baby. Who would like to read the next paragraph?
Natty.
Okay.
Why am I saying my name? That's what I have come to.
I just want to do it on beat. Our senior producer is Carolyn Foley, and Teach Me About the Great Lakes is produced by Megan, Lake Lover Gunn, and Renee Miles. Ethan Chitty is our associate producer and fixer, and our coordinating producer is Ava Hale. Our super fun podcast artwork is by Joel Davenport. The show is edited by Sandra Svoboda.
And if you have a question or comment about the show, please email it to teachmeaboutthegreatlakes@gmail.com or leave a message on our hotline at 765-496-IISG or 4474. So 765-496-4474. If you want to send us a postcard, we love postcards. That's 195 Marcellus Street in good old West Lafayette, Indiana, 47907.
There it is. 47907. 4797. Anyway, thanks for listening. Keep grading
Those lakes.
lakes.